Apparatus needed for performing this practical is Pasco mechanical vibrator, Pasco interface, string, mass hanger with set of masses, ammeter rod, electronic scale, 2 wire leads, pulley, 2 metal stands with the brackets. So from the figure, it's clear that we have the Pasco interface, and this Pasco interface is connected via these 2 wire leads to the string vibrator. One end of the string is connected to the vibrator, and this string passes over the pulley. The other end of the string is connected to the hanger having different masses, and this whole arrangement is placed on a table. This beautiful picture is of our lab is taken from the video uploaded by Dr. D'Oliveira regarding this lab. And what we are going to do is we have to connect this Pasco mechanical vibrator with the stand and connect one end of the string to the Pasco mechanical vibrator, and this string should be passed over the pulley, which is connected to the mass hanger, and the set of masses are present there. Connect this mechanical vibrator with the Pasco interface with the help of these 2 wire leads, and this Pasco interface should be connected to the computer system. So after connecting the Pasco interface to the computer, open up the template and select the signal vibrator in the menu located in the left corner. Click Open Controls of the signal generator and select the frequency to be 60 Hz and amplitude to be 6 volt. So switch on the generator using the on-off button, and once you switch on it, it will start, the mechanical vibrator will start vibrating, and we will see the standing waves in the string. So before proceeding towards the practical performance, let's move towards the part C, which is the questions and the description. So from the part 1 of the lab manual, first question is identify all nodes by making them with the letter N and all anti-nodes by marking them with the letter A in the standing wave pattern. You have the standing wave pattern, and I hope now that you know what are anti-nodes and what are nodes. We already discussed that the points where the amplitude is maximum are the anti-nodes, and the points which remain stationary and which have zero amplitude, they are nodes. So I hope that it's not difficult for you to point out where is A and where is N. Part 2. Fixed frequency with the different tensions. Now what we are going to do is we have all the experimental arrangement, and we will apply different tensions on the string. But before applying the tensions, we have a question. Question 2. In the last experiment, you investigated the relationship of wave speed with tension. What did you conclude from that experiment? So in the previous experiment, you worked out what would be the relationship of the wave speed with tension. For your help, I may introduce a formula that we have V equals to under root of tension divided by mass density. So you can conclude what's the relationship of this. Before proceeding towards the other questions of part 2, that is fixed frequency with different tensions, let's look a short clip taken from the video uploaded by Dr. D'Oliveira and Dr. Brian Thoms about this lab. And we will know that what's going on if we increase or decrease the tension when the frequency is fixed.
So that's a fairly low value for the tension, and you can see the standing wave pattern you get there. Notice that pattern and how close together the nodes and antinodes are. Now he's going to begin to increase the tension again as he pulls harder. Now what do you see about the distance between nodes and antinodes, and how many segments we get on the string as he pulls? And he's pulling a little harder. Yeah, there we go. That's a nice pattern, and he's continuing to pull a little bit harder.
Okay, so question 3. What happens to the number of antinodes as you increase the tension? We know that number of antinodes are equal to the number of segments. And from that video, you may see that if the string is pulled harder, that is when tension has been increased, what happened to the number of segments, whether they were increased or decreased. If they were decreased, that means that number of antinodes have been decreased. Question 4. What happens to the wavelength as you increase the tension? We know that wavelength has an inverse relationship with antinode. So if antinodes have been decreased by increasing the tension, that it means wavelength will be increased. Tension and wavelength will be directly related if wavelength and antinode are inversely related to each other. Refer back to the figure on the first page to see how wavelength is related to nodes and antinodes. Question 5. Does the frequency of the standing waves change as you increase the tension? And question 6, what is the justification to your answer? So you have to keep this in mind, that the relationship between the tension and the speed. You know that there is a direct relationship of tension and speed. If tension is increased, then the speed also increases. But we have speed is equals to f lambda. In this equation, two values will be changed and one will be constant. So by increasing the tension, you know that there was a change in the wavelength. If the change in wavelength occurred due to the frequency, due to the speed of the wave, then the frequency will be constant. Do you think so? Ponder on this and you will get the answer. Question 7 of part 2, fixed frequency with different tensions. So question 7 is that adjust the tension until the string vibrates with 4 segments. So you have to increase the tension so that the wire has 4 segments now. And explain how can you tell the displacement of the medium is 0 at the nodes. From this figure, you know that this is a good node and this is not a good node, which is not being made at the end of the loop. So I think you know enough things about the nodes, why nodes are formed, and you can easily answer this question, that why the displacement is 0 at the nodes. Question 8, measure and record the length of the segment or between the two adjacent nodes using meter stick. So when we have 4 segments, then you have to measure the distance between the 2 nodes, or the distance between the 2 nodes is equal to the length of the one segment. So find out the length of the segment. And question 9, determine the wavelength of the standing wave with the meter stick. Now you know this thing, that wavelength is equals to how many segments? So if it is one segment, then how many segments you have to measure to give one wavelength value? You have to measure number of segments which are in one wavelength.